So class, today we will be studying circular shift property. In the last session, we have discussed about the property of circular shift. Here, in the property of circular shift, if we take DFT endpoint DFT of a signal of g of n minus n naught modulus n, it comes up to be Wn to the power k n naught into gk. There is a resemblance between the properties of DTFT and DFT. If we move back to the time shift property of DTFT, we will see it is the same as the circular shift property, only that e to the power minus j omega is replaced by Wn, and every other notations remain the same. Same is the case with frequency shift. Previously in DTFT we used to denote it in terms of e to the power j. Here we denote it in terms of Wn. There can be only one change, that is in the signs of powers of Wn. But here the change is due to the factor that Wn itself has consumed a negative power. So there is a change in the polarities of Wn, powers of Wn. Everything else remains the same, and the proof is also the same as we have done in case of DTFT. Here another property is the circular convolution property. Before we move to the property, we need to know what circular convolution is. Previously we have studied only convolution, but here as we have come across circular convolution, the term that we have studied previously as only convolution will be renamed from now onwards as linear convolution. So we have two convolutions now, linear convolution and circular convolution. The formula for linear convolution was Gn convolve Hn. It was equal to summation k going from minus infinity to infinity g of k h of n minus k. But here we know there is a limit in the band of vision of DFT. We cannot move beyond 0 to n minus 1. So the limit in our circular convolution will be m going from 0 to capital N minus 1, g of m, h of n minus m, but due to circular shift you have to use a modulus n. This is our new convolution formula for circular convolution. And if you take its endpoint DFT, we will have the individual DFTs of Gn and Hn, that is Gk and Hk multiplied, as is the case in every other transformation methods. The last property is the Parseval's relation or Parseval's theorem. The proof is what I leave on to you people. Now we need to know how to solve circular convolution. There are various methods of solving circular convolution, as we knew the various methods of solving linear convolution. The first method of solving circular convolution is the graphical method. Let us take an example to show how we solve circular convolution with the help of graphical method. We have to first keep in mind the formula for circular convolution, which is written here. There has to be a suffix n here, which is missing here. Now m goes from 0, 1, 2, 3 because the length of the signals that we have taken are 4. Here we have taken Gn as 1, 2, 0, 1 and Hn as 2, 2, 1, 1. So if Gn is 1, 2, 0, 1, we can write Gm also 1, 2, 0, 1 and Hm also as 2, 2, 1, 1 as we have done previously in the case of linear convolution. Now according to the formula, first what we have to do is find out h of minus m, keeping n is equal to 0 if we need to find yc0. Here we have used c because we want to find out circular convolution. We have put n as 0. The first thing that we have to find out is h of minus m. We cannot forget the modulus, which is 4. That is, first if m is 0, we have h0 which is in our range. So h of 0 comes down. Now if it is h of when m is 1, we have h of minus 1. Minus 1 is out of our range. To bring back to our range, we add plus 4, that is h of 3. So h of 3 comes in the position of h of 1 for h of minus m. In this way, if you have h of minus 2, which is again out of our range, we add plus 4, that is h of 2. So h of 2 comes down in the position of h of 2 in the case of h of minus m modulus 4. And what is h of minus 3? If you add plus 4, it will be h of 1. So h of 1 comes down in the position of h of 3 in case of h of minus m modulus 4. So we have got h of minus m modulus 4, we have got Gm. We can multiply each of them and add them. So yc0 comes up to be 6, that is 1 into 2 plus 2 into 1 plus 0 into 1 plus 1 into 2, which comes up to be 6. Now similarly, if we want to find out when we put n as 1, when we want to find out yc1, n becomes 1. So we need to find out h of 1 minus m modulus 4. h of 1 minus m modulus 4, if we found out, or what we can do is we can rotate, make a circular shift of h of minus m by plus 1 position. So what happens? For h of minus m modulus 4, we make a circular shift. We bring back the last component, that is h of 3 for h of minus m modulus 4 to the first position for h of 1 minus m plus 1 minus m modulus 4. That means we make a circular shift of h of 1 minus m modulus 4 to find h of 1 minus m modulus 4. So the circular shift is shown, the pattern of circular shift is shown. Similarly, again we can multiply each of the components, add them to find hc of 1 as 7. Similarly, we can find out yc2 and yc3. The output and all of the circular patterns I have shown here. h of 2 minus m is again a circular shift of h of 1 minus m modulus 4. h of 3 minus m will be circular shift of h of 2 minus m modulus 4. All the circular shifts are shown by the arrows, and then you have to multiply the individual components and add them to find the circular convolution as the formula suggests. Class, thank you for today. In the next class, we will study another method of solving circular convolution. Thank you.